The formula for parametric differentiation. Welcome back. Let's begin by looking at the formula for parametric differentiation. To start, let's recall what we covered in the previous subsection. We established that parametric equations are a bit different from standard equations because they express both x and y as functions of a third variable, which we call t, or more formally, the parameter. Now, as we move into the calculus aspect of this topic, our primary interest is usually to find the rate of change of y with respect to x in your notes. You'll see this denoted as di by dx. However, we run into a slight problem here. Since y is not expressed directly in terms of x, we cannot simply differentiate it in the traditional way. To overcome this, we use the chain rule. This allows us to create a mathematical link between x and y by using the parameter t as the bridge. In the next few slides, I will walk you through the theoretical derivation of this formula and show you how to apply it step by step. Theoretical derivation of the formula. Now that we have established the need for a link between our variables, let us move on to the theoretical derivation of the formula. To understand how we find the derivative of y with respect to x, let us consider y as a function of the parameter t, and in turn, consider t as a function of x. By applying the chain rule of differentiation, we can express the derivative of y with respect to t as the product of the derivative of y with respect to x and the derivative of x with respect to t. In other words, di by dt equals di by dx multiplied by dx by dt. To be clear about the components of this equation, di by dt represents the rate of change of y with respect to the parameter t, while dx by dt represents the rate of change of x with respect to the parameter t. The term we are actually searching for is di by dx, which is the derivative of y with respect to x. To isolate our target, di by dx, we simply divide both sides of the equation by dx by dt. This gives us our primary formula. Di by dx equals di by dt divided by dx by dt. Alternatively, if we prefer to use function notation, where we represent x as f of t and y as g of t, the formula can be written more concisely. In this case, di by dx equals g prime of t divided by f prime of t. However, there is one critical condition you must keep in mind. This formula is only valid if dx by dt is not equal to 0. If dx by dt equals 0, we would be dividing by 0, which means the derivative di by dx is undefined at that specific value of t. We will see later how this relates to the geometry of the curve. Real-world analogy, particle motion. Now that we have established the theoretical derivation of the formula, let us move to a real-world analogy to help you visualize what is actually happening. Imagine a particle moving across a flat surface. At any given moment in time, which we represent as t, the particle's position is defined by two separate coordinates: its horizontal position, x, as a function of t, and its vertical position, y, as a function of t. If we look at the rate of change of the horizontal position with respect to time, we are essentially finding the velocity in the horizontal direction, which is denoted as dx over dt. Similarly, the rate of change of the vertical position with respect to time gives us the velocity in the vertical direction, denoted as dy over dt. Now, if you want to determine the slope of the actual path the particle is carving out, which is the derivative of y with respect to x, or dy over dx, you simply divide the vertical velocity by the horizontal velocity. Essentially, this ratio tells you exactly how much the particle moves up or down for every single unit it moves across at that precise moment in time. With this conceptual intuition in mind, it will be much easier to apply the formula to mathematical problems, which we will explore in the next slide. Step-by-step application. Now that we have covered the theoretical derivation and the conceptual analogy of particle motion, let us move on to the practical application. To calculate the derivative using the parametric formula, it is best to follow a structured, step-by-step approach to ensure accuracy. Let us look at this example. We want to find the derivative of y with respect to x, given that x equals a times t squared and y equals 2 a t, where a is treated as a constant. Step 1 is to differentiate x with respect to t. Given that x equals a times t squared, we apply the power rule of differentiation. This gives us the derivative of x with respect to t, which is equal to 2 a t. Step 2 is to differentiate y with respect to t, since y equals 2 a t, and we are differentiating with respect to t. The derivative of y with respect to t is simply 2a. Step 3 is where we apply the parametric differentiation formula we discussed in the previous slides. We substitute our results from Step 1 and Step 2 into the formula, placing the derivative of y with respect to t in the numerator and the derivative of x with respect to t in the denominator. This gives us the derivative of y with respect to x as 2a divided by 2 a t. Finally, in Step 4, we simplify the expression. By canceling out the common terms, specifically the 2a in both the numerator and the denominator, we arrive at our final result. The derivative of y with respect to x is equal to 1 over t. As we move forward, keep this process in mind, as the next section will highlight some common pitfalls students encounter during these specific steps. Common mistakes to avoid. Now that we have walked through a practical example, let us discuss some common pitfalls to ensure you avoid these mistakes in your assignments and exams. First, let's address the issue of inverting the formula. A very frequent error is to accidentally divide the derivative of x with respect to t by the derivative of y with respect to t. To prevent this, always keep your objective in mind. Since we are searching for dy by dx, the derivative of the numerator, which is y, must remain in the numerator of your fraction, and the derivative of the denominator, which is x, must remain in the denominator. Secondly, some students may be tempted to ignore the parameter entirely. You might feel inclined to eliminate t first to find a direct equation relating x and y before differentiating. While this method is mathematically valid, it is often algebraically tedious and prone to errors. The parametric differentiation formula we have just applied is specifically designed to bypass this necessity and simplify your workflow. Finally, it is important not to forget the logic of the chain rule that we established at the beginning of this lesson. Remember that dy by dx is essentially a ratio of two different rates of change. This is why, as we noted in our theoretical derivation, if the derivative of x with respect to t equals 0, the slope of the curve becomes vertical and is therefore undefined. Recognizing this is critical, especially when you begin sketching these curves. Keep these warnings in mind as we move to our final slide to summarize the key takeaways. Key takeaways. To wrap up our lesson, let us review the key takeaways to ensure you have a solid grasp of parametric differentiation. First, let's revisit the core formula. When both x equals f of t and y equals g of t, the derivative of y with respect to x is calculated as the derivative of y with respect to t divided by the derivative of x with respect to t. As we explored in the theoretical derivation at the beginning of this session, the basis of this formula is derived directly from the chain rule. Regarding the requirements for this formula, please remember that the derivative only exists when the derivative of x with respect to t is not equal to 0. As we noted in our discussion on common mistakes, if this value is 0, the slope becomes vertical and is therefore undefined. Finally, let's summarize the practical process we applied in our step-by-step example. The workflow is always the same. First, find the derivative of x with respect to t. Second, find the derivative of y with respect to t. And third, divide the two results to find your final answer.